Hello viewers, today I have a very nice pair of instruments here. They come from a jet plane, a DC-10. They were manufactured in, let me see, there is a date. The last service on this unit was in 1997, as you can see here. Warranty may apply. Oh no, this unit was serviced. Okay, may apply. Okay, late 90s. This one is a so-called RDI, radio direction indicator, and the other one is a engine speed indicator, which shows you the RPM of the engines in percent. So you have a scale from 0 to 120%. Of course, you shouldn't work the engine too long over 100%. I don't know the flight manual of the DC-10. You can certainly find it somewhere and read about these instruments. What I want to show today is what's inside, because there are a couple of very interesting parts inside I want to take out, and I have the plan to make a clock with this instrument here. And maybe this instrument here will also help me doing this. Now I want to start with this instrument here. You see, it's a relatively small instrument. The DC-10 has 3 engines, so this is the instrument from one of the engines. They all have the same instruments. It is made by General Electric. Here is the dust cover. We don't need that anymore. Is there something interesting? I don't know. Serial number, okay. Power input 4 volt and 115 volt at 400 Hertz, one phase. Okay. Range 0 to 125%. The weight is also indicated. Maximum weight 2.4 pounds. Weight is always an important thing when it comes to aircraft parts. So everything must have exactly the weight that is indicated, or you get out of balance with your aircraft, and that's a bad thing. 2 lamps, General Electric, part number blah 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 blah. That's a little bit funny here, because the lamps, you can pull out the lamps here, and if you have to change them, you can see the light bulb here, and for working position you push it in, and then it illuminates the scale, the dial here, and the arrow, the pointer. There is a little knob, it's fallen off because I had to drill out the screw here. Unfortunately, I didn't have the right key. It's a Bristol multi-spline screw head, and I have a couple of these tools, but I didn't have exactly that size here. So if you pull that, oops, if it's possible, no, I pull it like this, then you see there is a black cover here that moves up, and then you see a number 24.8. If you turn that, you can go up to 132. I tried that before. I have no idea what exactly that means. I think it is probably to set a limit, a maximum limit or something like that. And if your engine reaches that limit that is set here, some kind of signal or alarm or maybe a warning light goes on, I don't know. You probably find this information somewhere in the World Wide Web. I don't bother to search for that. So we want to see inside. So the first thing we have to do is to remove 3 screws. I have already done that. Then this plastic cover comes off. Then I need a tool here. Where is my tool? Where is my tool? Which one do we take? This one is fine. So we have a rubber gasket here. I take this out. And then, well, the only way to get the inside stuff out, because here on the front this is fixed to the case, you cannot remove that front part here, so that must go somehow like that. Yes, it comes. And well, I have already tried that before, and that's the reason why I had to remove the knob in the front, because the axle from the knob goes through this hole, and when the front is when the knob is in place, you can't slide it out. So making a bit a nasty sound. Now what I am surprised here is the length of this instrument, because you only have this small dial here. It's about 3 fingers wide, but look at that. There's a whole bunch of electronics on the back. A really dense construction. It looks like the top board here is some kind of power supply, DC converter, maybe a rectifier stuff. We can have a closer look at that later. You also see it is a little bit brown here in this region, so I guess that has become a little bit warm. But after such a long time, that's quite normal to have a little bit of discoloration of the boards. So what do we have here? That looks a little bit like microprocessor stuff. Here's a nice white ceramic package. Yes, quite a bit of electronics for a engine speed meter. Then, oops, that comes off. That is only the glass. Okay. So what do we have else? So here's the electronics. Here is a big, I don't know, looks a bit like a transformer or something. Maybe just a coil. There are a couple of white wires here. The flex cable here goes to these motors. I think that's just 1 or 2 stepper motors, probably. Maybe it is also possible that these 2 motors here are so-called synchros, or well, I'm not sure what the English name for it is. Synchronous motors. It's some kind of a 3-phase motor, which is coupled to a similar 3-phase sensor that is probably mounted on the engine. So this instrument comes from an era where the electronics in the airplane have been on a very minimum. So this is more like mechanics than electronics. They have, of course, some computer stuff here. So I guess it's also possible that these are just like stepper motors, but it's not sure. So what I find the most interesting part are these numbers here. So you can see they just turn free when I touch it. It's like on the display here, there's a red bar. That means that the value you can read here is not valid, because the entire unit here is not powered up. When you power it up, this red bar here disappears, make the numbers below visible. So the interesting thing is, I don't know if it's the same as in the other instrument. In the other instrument, the numbers here, they have 10 wires coming out on the back side, and there is 1 wire for each number. So if you power up wire number 3, it jumps to 3. And when I look at the number of wires here, this could be a similar construction. We will see later when I take it apart. Now there is also a nice blue thingy that looks a little bit like a motor. The axle comes here. It could also be a potentiometer, because it is manufactured, I don't know if you can see that in the camera. You can clearly read the name Burns, and Burns is a traditional big manufacturer of all kind of potentiometers and switches and electromechanical stuff. So let's zoom away a bit and have a look what we can do. So I hope I'm still in the picture, yes. So these are the lamps. They are just 2 wires and a sliding mechanism here. You slide it out, you can remove the lamp, which looks like this. Oh, maybe. Okay, 2 wires, little lamp. You find this in instruments or maybe in small torch lights or flashlights, however you call that. Second one. How do we start? I have never disassembled such an instrument before, so I have no idea how this goes. Okay, that comes out. Very nice. There is a rubber around it to hold all these cables down. That's a very interesting solution. So I just cut that away. Then maybe I have to zoom in a little bit. That one comes out. I don't know if I'm doing this right. Maybe some people will get angry when I do this with brute force, but I don't intend to use that again. So we have here a dial that turns around. Oh yes, there was a, where is it? there was a little indicator that has fallen off. Okay. It looks like this, just an orange pointer triangle. I think it is broken away from that ring, so if we turn that ring, that pointer here will move around like that, and indicating something important, maybe the maximum engine speed. So these cables go here to that flat flex cable. They are soldered just here, so that part of the flexi cable here is only for the illumination. So I'm a bit impatient, so I cut this through here, and maybe again here, and a little bit here. So illumination, there is two other conductors. They go to something that looks like a solenoid thing, maybe a relay, maybe no, not for this one. So I have seen the lamps. Okay, lamps can go, thank you. We have some nice mechanical parts here. Oops, let me adjust the camera a bit. Okay. So if I move that, you can see the gears are turning. There are all kind of gears turning, and it's also turning the axis of the first motor here. It's about here. You can see that turn. There is a screw that attaches the motor axis to the rest of the mechanics. Then we have a very nice gearing system here. And I turn that axle from the front knob. You can hear the clickety-clack. You can also see how it counts up. 80%, 90%, 100, 120, and then at 136 it stops. It has a mechanical stop, so it can't go any further, which is possibly not necessary. Okay, I think I'm a little bit low with the light. Okay, we have gears. We have very interesting gears. Let me show you that. You can see there is one gear. So this is when you pull the axle. This is when you push it back. You can still turn it. I don't know if that is correct. Maybe it's a problem. Here down here you see the axis that spins the numbers. You can also see the numbers going around. Yeah, pretty nice mechanics here, like a clockwork. So let's do some brutal stuff. I need some pliers. Okay, we have a nice little connector that goes directly to this flat cable here, so you can see all the input connections. Very nice. So this is, oh, there is something written. Reverse, what? Reverse, rare, other side. Here only 16 pads. Okay. Reverse, spare, other side. Here only 14 pads. So they have written on the cable on how it has to be mounted here, which is a very nice touch for the people who have to assemble that. So there is also a nice detail. They attach some O-rings here, some rubber rings around these corners, probably to avoid vibration. On all the boards around. Nice little rubber rings. So, but we still can't remove this transformer here, which bothers me a bit. So we have all the boards loose on this side. There is an additional strengthening pin that goes through all the boards. I don't know if you can see that. Yes, a plastic pin goes through all the boards and holds them together. So from the shape of it, I would say you simply turn that to one side and remove it. Yeah, that's it. A simple twist and lock mechanism. So we have separate boards. Now they are screwed in place here, so I have to open to remove that one, which is a little bit tricky because the screw seems to be a bit old. Okay, it's out, so we probably can, yes, remove the first board. So this is a quite simple card edge connector, not too fancy. You can see the contacts here, the spring-loaded contacts. I think that's something you could find in a lot of other electronic stuff. Maybe not in the cheapest ones, but it's not too specific for aircraft instruments. Well, a little bit it is a little bit special because it's quite narrow here. You can see it's not very thick, so it's made to preserve space. So we have another board which we haven't seen before. Let me see, here we are. We have two big black chips, two big silver chips here, and a couple of transistors, and surprisingly some unpopulated space here for a little dip chip, a little round chip. These are not transformer op-amps. They look like, what did I say? They are not transistors. This is a transistor probably. These look like op-amps with 8 pins. Let's see if we have a number. LM741. Yes, that's a classic. The good old 741. What do we have here? General Electric. 6900W12 P006 date code 8542. So we are already talking about the mid-80s. Okay. DA1, DA2. Oh, there is maybe a hint what it could be. DA1 and DA2. Maybe that's a digital to analog converter, which does make a certain sense, maybe. We have here an MH250. Can we focus that? Yes. For all those who want to check that out. Maybe we can also see the writing on the silver can here. Yes. Okay, let's go to the next board. These screws are really a bit a pain. And they are also non-magnetic, like the most stuff in airplanes, because even if they have all kind of electronics, they still have a magnetic compass. So if everything fails, you still have the compass to tell you in which direction you fly, and they don't want to distract that compass with magnetic stuff lying somewhere around. So what do we have here? Some nice chips. You see it first, I look at it a little bit later. We also have DA3 and 4, maybe another digital to analog converter. Some nice ceramic chips with holes inside. There is one with a golden cover and the crystal. So the golden cover says LIA. Oh, I have to get my glasses or my magnifying glass here. So what do we have? LIA 2361 6900WII or 11. Manufactured in 87. Whew, no idea. Could be a digital to analog converter or analog to digital, I don't know. What do we have here? S8822F. Some logic chips, perhaps. S8022F. And that one I can't read. Something made in Indonesia. I really can't read that. Well, okay. What do we have else here on the board? Some caps, some resistors, some diodes. Okay. Not too exciting at the moment. Maybe we find out some more details. So this is the second last board. They also covered the screws with some paint stuff, glue, vibration protection. So that's another nice, but it looks a little bit like an old Tektronix oscilloscope, a Tektronix from, well, 1960s, 70s, with one difference: the Tektronix always had golden conductors, and this here have. What I'm surprised that they have no coating on the board, on the parts. Normally, these precision instruments, especially those that go into an airplane, are coated around against moisture and all that stuff. But maybe in modern airplanes this is not necessary anymore. They managed it to make the airplane watertight or something like that. Well, I give you here a little close-up view of this board. It's mainly transistors, diodes, capacitors, a lot of operational amplifiers. Which one do we have here? Is it the 741? Maybe, maybe not. It's 741, and that one is another 741, and oh, a 741, what a surprise. 741, it's a little bit boring. This one is, well, I think that's all a little bit the same stuff here. Well, they just have to get some analog signals to adjust some voltage levels and maybe send it back to the engine or whatever they do. So let's see if we can remove the last board too. Oops, I'm almost out of camera limits. That's better. I have to rearrange that camera one day, so it's not optimum where it stands now, but it's not too bad. So what do we have here? Some trim pots, some 741 op-amps, and 2 chips. What's written on them? S8822F, I think we had that before, S8822F. Maybe a custom made thing, maybe just a bunch of AND gates, NOR gates, whatever. So we have some nice, I think, precision resistors, the black ones here, some capacitors, trim pots. Yeah, not too much magic. That's the board on the top with the brown spot. I think when we look at the big capacitors, the transformer here, so I think that's more or less the power supply. We have more 741. Is it true? Yes. So they had a contract with the 741 op-amp manufacturer. So, but we still don't get that transformer out. Ah, there are more screws. I think we have to remove more screws. Okay. Oh, that one is nice. Really? Yeah. A screw with its own little security nut. It's a self-securing nut. I have to hold that because it's not possible to remove that without the pliers. I think Phillips screws have not invented yet. Oh well, they were, but they decided not to use them for whatever reason. But they decided to take unnecessarily long screws. So yeah, is that nice? A nice little self-securing screw. If it's metric, I would say it's a M2 or an M1.5, I don't know. So, but there's another one on this side. I wonder what they hold down here. So we have to remove that too, maybe. It's also screwed into this metal plate here. So we have another screw and a bolt and a nut. Nuts and bolts, watts and volts. Yeah. Oh, there's another screw. Okay. Let's remove that. Now we get into the heart of the beast. No, yes, that's just an insulator between the folded. There's a nice folded. Oops, something has fallen down. Oh, just a piece of plastic. So this is a protection for these flat cables, that they are not penetrated by these solder pins here, because it's quite densely packed. And as we know, airplanes do always vibrate, especially when they fly. So where is that going? So we can remove the long screws here finally. So they are out of the way. Number 4. So it has a General Electric part number on it, I guess. So let's see what's underneath here. There is, I have to rip that apart. Okay, maybe I don't have to, but I do it anyway. So we have 2 white wires. They look like they have forgotten this in the flat flex design, or they are just for higher current. So now you can see it. There is quite a bunch of connectors. So this is clearly some kind of transformer. Very nice. This transformer is of course made for 400 Hz. That's the frequency you use in airplanes. And the reason is relatively simple. The higher the frequency, the smaller the transformer you have to make. So you need less iron, you will need less windings. So that's the reason why they went to 400 Hz. Maybe they could have gone to a kilohertz, but in the early days I think that was already high frequency. So there is the lever for this red bar. It's like around here. I think that's just so how is it? Oops, more nuts falling out. How is it driven? So now this screw here is hidden behind this switch, and this is really a micro switch. You can see the green switches here, and they are activated when I push or when I pull. When I pull it out, the switches do close. I hope you can see that. Yes, I think that's not too bad. You can also hear the clicky sound. Nice. So we have another arrangement of switches here, which is quite funny because there is a screw slot that is accessible through the front panel. There is a little hole in the front panel. You don't see this screw by eye, but if you turn it, you can see that brass cylinder there, which is a little bit eccentric, and it closes two switches and opens the other one on the other side. So I think that's for the service personnel to adjust something. Okay, how do we proceed? Oh, there's another screw. Okay, let's open that one. Another screw. I think I have to make two videos of these two instruments because it takes a little bit longer than I expected. So, no more screws. Still holding together, which is a little bit frustrating. There are more screws. Okay. Maybe we have to start from the back. Oops. You always slip out of these screw slots here. Torx would be fine, guys. Well, I think Torx was not invented in 1985. I don't know when these Torx screws came up. They are relatively new, but I also may be wrong with that. So how long are they? Oh, they are extremely long. And we are generating some metal shavings here. So what is the trick? Do we have to pull that? Yes. Ooh, that's the trick. They are really, really long. So there's another one. Yes, sir. It comes out. And there's the third one. Yeah. So, and I think we already have. Oh, what's that? Oh. That's nice. So let's see if you can see that. I have already mentioned that solenoid thingy here. So it seems that is some kind. Is it some kind of brake? Okay, it goes up. So when it's energized, this will go up and that too, and then what is this here? This turns. Okay, but I think that's some sort of brake. So I don't know exactly how it works. So there is a magnet, an electromagnet. There are the pole shoes here, although it looks like aluminium, and then it pulls up that one, loosens that and makes that turn, and if the electric energy is cut off, this spring here will pull the two arms together, and then it clamps this. And what is it doing? That's the little red indicator here. I think that's the indicator that is set to something. So how can we get that annoying horn? Okay. And I think when it is set, it must stay at that position, and that's what the brake does here. So let's see, we have another screw here, which seems to be a little bit shorter, well, shorter than the other one. So this motor here is already loose, but it is still connected somewhere to the rest of the mechanics. So what do we have here? Oh, did I say they had no torques in those days? Well, that looks like no. It looks like the hex Allen key, how some people call that. Let's see if I have the right one here. Oops. It's a little bit difficult because the axis turns away. No, that's too small. One bigger. I guess that's too big. Yes, of course, I need something in between. Let's try a Torx, even if it is possibly not a Torx, but you can always, yeah, that one goes very well. You can always use a Torx to open a hex screw. So let's have a look at this. What is it? It is certainly, no, it's not a Torx. It is a normal 6-corner hex screw, but if you have the right Torx, it fits quite well because it goes exactly into the corners of that screw. So what happened? Yeah, that was it. Here you have a motor with this axle. Ooh, a very, very nice construction. Oh, it's not a motor. Now I see it. It's a rotary switch. So you can see, and it is spring loaded. It goes back to a certain position. Oops, sorry, I was out of the camera. So I turn it in one direction and the rest it goes back by itself. And there you can see there are some sliding contacts here. Yes, that slides around on that PCB part. Ah, there is another slider out here, and that looks like it is sliding on a carbon track. So I don't know if you can see that. There's a black carbon track underneath this finger contacts here. So this is a potentiometer, or maybe a little bit more precisely a angular position detection sensor device stuff thing. Okay, we have more screws. Let's care about those. So this is certainly to remove that brake assembly, or at least the solenoid that drives it. Oops, yeah, it came off. So we have a solenoid with 2 pole shoes on the end, and we have these 2 brackets that break. Oops, what was that? Oh, that was the spring. Okay. Well, it's like more or less a brake on your car. If you have an old car with the drum brakes, it's a similar construction. So we have 2 axles here. One is hollow, the other one is inside the hollow axis, so that is the little brake assembly. It's a little bit, well, it's plastic. It's not rubber, but it looks like rubber. It's a plastic thing. So to get a good grip. So there we have another nice, even smaller hex screw. No, still too big. Going to a Torx 5, which is very small, which is too small for this. So I don't give up. I also have some hex inserts here. Oops. Oh, jumped over a certain point. Okay. Ah, there is a. Okay, that's nice. There's a mechanical stop here. This spring type here. That is a stop. And there is another stop on this side. And it's not a hard stop, it's a flexible spring, as you can see here. It moves a little bit. So if it goes very quick back, so it doesn't stop too hard, which is very nice, but I still can't open that. On the other side there's not much. Serial number, a logo of the manufacturer. Don't know what it is, I have never seen that before. So, but I don't think that's everything, because we have here the contacts for this switchy thing. We have, that's the contact where the lights, the illumination lights, the bulbs have been, so that's only that. But there is some magnetic wizardry here. Okay, more screws. I just found another screw here. Maybe we are lucky and we find something. More screws. My screw collar. Yeah, it moves. It moves. It moves. It's loose, but it doesn't come off because I can't remove that part here, which is annoying. That's too big. That's too big. Maybe that one. No, too big. Too big. That one. No, doesn't fit. Okay, let's go the old-fashioned way. Let's use brutal force, but that could be difficult because it looks very stable. I use my pliers as a hammer, which is completely wrong. I know that, but I do it anyway. Okay. Yeah, it would be so easy if that part just came off. I think I will ruin my good screwdriver here. Oh, now the plastic is breaking. Very, very well made. So that is the hollow axle, which is still there. Yeah, it comes a little bit. So what's inside here? What's that? So I mean, there are something like magnets inside, but okay, there are wires going down. Okay, so I need a hammer Brute force method. Ouch, ouch, ouch. Oh, it goes boom, it goes wrong, it goes but. It changed a little bit here. Don't look how I use my tools. It's horrible. Yeah. I see a couple of coils. So I think we have some kind of synchro motor here. Synchro, how do they call that? Synchro resolver, maybe. So now I have removed that part without loosening the screw, and everything gets very easy. So we have 3 coils in a 120-degree arrangement, and there is it the magnet inside? Oh, there is a little bearing, a ball bearing here. Nice. Instrumentation, precision ball bearing. So how do we get that away? Oh, okay. Oh, there are some wires. Let's snip the wires. And yes, I can tell you this is a magnet because it holds my pliers here. Quite a strong little magnet. So there is not much more, just a magnet, an axle and a position sensor, and we have these 3 coils. Now the theory is, because this instrument is only using a 1-phase current supply, well, to make it short, it's not maybe not correct in detail, but if all 3 coils get the same amount and the same phase of current, this will not move. But if for some reason the voltage or the phase, I don't know which one is more, I think it's more like the phase that makes the thing turn. So if these 3 windings go out of balance, this magnet starts to turn. And I think I have to set up another experiment. You can actually use 2 of these synchros, how they are called in short. So let's put that together. You use 2 of them, wire it one to the other. You apply a 400 Hertz voltage, maybe in this case 115 volt, maybe it's also transformed down to a lower voltage. And the funny thing is, if you connect them together correctly, if you turn one, the other one will do exactly the same rotation by itself. So this was used in older airplanes, or maybe even in this airplane, to get signals from one end of the airplane to the cockpit, for example, for an instrument. So just imagine you hook up one of these synchros to the engine, and it turns with the engine revolution speed. You only need 3 or maybe 4 wires, I don't know how many wires you need. Well, you only need 3 wires because the other tools are just the power supply. You can supply the power from another point. You need 3 wires. You go to the cockpit. You go to a mechanical speed meter, and the axle in this meter will have exactly the same number of revolution per second as the pickup transducer, if you want to call it like that, in the engine. So instead of using a flexible shaft, which you can do, for example, in a car, if you have an old car, there is a flexible shaft that goes from the engine to the, for example, to the speedometer. How do you call that? Tachometer. And instead of using a flexible shaft, which is a little bit impractical in an airplane because you have to go 20-30 meters with a mechanical flexible shaft, that's not possible. But this is the electric way of creating a flexible shaft. So you have a transmitter, you have a wire, you have a receiver, and they do exactly the same mechanical revolution. Well, that was maybe a little bit complicated, but maybe I'll make another video to explain that a little bit more if I find the right parts for it. So here we have something else. What does this do? This drives the outer ring. So you can see if I turn that motor here, the outer ring is moving. Okay. So I just destroyed the outer ring. It's just a piece of a plastic gear with a glued on dial. Then there is a piece of metal, and that's the face plate of the instrument. Oops, which I have just bent. It's very, very thin here. So let's see, do we have a Phillips driver? Yes, a black screw on a black panel with low light. Okay, that comes off. Has some date code stuff, maybe a part number. Everything has part numbers in airplanes. So how do we get there? More screws and more plastic parts. 1, 2. 2 more screws. Oh, there's a third screw. I didn't see it. It's so bright and shiny. I expected a black screw. Okay. Now, is it coming off or not? No, because there is a gear sticking through it. That's exactly where it's. So, but we can maybe turn it around. Yes. Oh, I just bent the axle of that gear. I'm a bad boy, destroying everything. There is a screw in this, but it's too small. I don't have such small tools. I need oh, that's a nice one. So this is the axle with the knob, the adjustment knob, and there is a spring, and it goes around here. and it goes around here. So this spring is in fact a torsion bar that pulls that back. So I think it should pull it back by itself, but it doesn't. So I don't know. I mean, this instrument has certainly seen better days. So there's something coming off. Torsion bar. There is something we can open from here. I think I need a little bit more light. So that's the torsion bar spring thing. Nice. Certainly a good quality. So now we can see there is the black shutter that covers the number. When they are adjusted, they should not be seen, and that's the gear that drives that number dial. 90, 80, 70, yeah, it's just working by itself. So I still have, there's another rod that we can screw away. Oh. No. A little bit more positive thinking. Oh, there's another part falling out. That's what I say. Remove all the screws and it will fall apart by itself. So that's a little bit tricky one. Okay, looks like that. Screw thicken. Now, now we can remove that, but that is attached to another ball axle here, which I cannot remove at the moment. No. Everything is connected to everything. I got the counter out. So now we can see that Burns thing. Hey, Mr. Burns. So we can clearly see it's a potentiometer. We have 3 contacts, which is nice. It is driven by the gears here. So this acts as another position sensor. In this kind, it senses the position of this dial here. So if you turn, when you turn that dial, you also turn the potentiometer here, and then the electronic, they called it a computer. I wouldn't call it like that. It's more like an analog computer. That tells the computer what you dialed here. So we have some gears. They just come out of their oops. Oh, nice one, nice one. A little bit hard to focus. They all have ball bearings here. So we can take that one out. Oops. Yes, nice. Oops, where are we? Here. Nice ball bearings. So if I keep them clean, I can reuse them. And there are nice ones with the flange, so they're easy to install. So that's a little bit hard to get. But this is what I wanted. So we have still this funny thing, which I don't know how it is driven. It's driven from that side, so this is just a counterweight to make it easier to lift. And the solenoid is certainly here in this silvery, yeah, it has 2 contacts. So that's the solenoid to lift up that, how is it called, that orange bar here. So now we have a lot of contacts here. 1, 2, 3, 4, 5, 6. We have 6 contacts for each number here, which is 6. 6 contacts for 10 positions. So I'd say one of the contacts is the common ground, however you call it. And then there are 5. To select the right number, I think I have to play with that, but first I want to get rid of this solenoid thing, but should I? Or should I just leave it? I leave it. Okay. We have 2 different flat flex connectors. There is one for 2 of the digits here. Just try it out. I start up my not multimeter, my bench power supply, which makes a little bit a noise. So what do we need? Okay, I take channel 1, and there was something about 4 volts on the back label, so I try that, 4 volts, and I limit the current to, let's say, 50 milliamps. So that should be safe. I don't expect that these parts need more current. So mini hooks. Oops. I have to adjust the camera a bit. It's a little bit difficult. Okay. Now I have to switch on the channel, of course. We don't have any voltage. Okay. Does it move? No. It draws 25 milliamps. No. It draws 2.5 milliamp, which is very, very low. No. Yes. 2.5 milliamp. Okay, it doesn't move. So let's go to 10 volt. Let's see if that moves. It's a little difficult to contact this. Okay. So it's freely moving. Okay. Now we have 5 milliamps. No, it's 50 milliamps. I really need my glasses. Okay, let's do 100 milliamp limit. Maybe we need a little bit more current to lift that. Okay, now it's 60, so we need a little bit more voltage. I have 10, let's go to 20 volt. 100 milliamps, so that should be enough. So maybe I have to change the polarity. Yeah, that's it. Okay, go back to 10 volt. Is it still working? Yes. You can see that, yes. Oops. Goes up, goes down. Oops, short circuit. So I think with 50 milliamps limit, that's way enough. Okay, let's see what it does with 5 volts. Yeah, still working. So I say it goes a little bit softer, but it works. 5 volt, 30 milliamps, 31, okay. 2 volt. No, 2 volt is not enough. 3 volt. No. 4 volt. Nothing. Okay, let's go to 10 volt and everything is working fine. Okay. 10 volt, 50 milliamps. Okay, now it's limiting. So I better limit the milliamps. I go to 20 milliamps. Is it working? Yes, 20 milliamps. We have 20 milliamps and we have 3.2 volts. Okay, why didn't it work before? I don't know. So let's reduce that to 10 milliamps. Okay, now that's an interesting effect. It jumps up and goes down. That's because there is a capacitor on the output of that power supply. And the problem is if you're going to low milliamps limit, this output capacitor discharges now, and when it is discharged, then it reduces the current back to 10 milliamp. But in the first moment you have a really high current. So let's see, 20 milliamps. Can it hold it? Yes, okay. So I would say, yeah, 5 volt about is okay. Current limit 50 milliamps is okay. So now we have to look at this turning numbers. So I will hook them. I have no idea which one could be the common pin. Is there a sign, something? No. Interesting. Manufacturing date 79. Even older. So it's a little bit difficult to hook the hooks on this part. So can you see that? So this is moving freely. Oh, I have one. 5, 5, 5. Well, it moves, but there's no difference when I touch. Okay. I go to the second pin with the yes, so I do all the combinations. But I think I have to desolder this because I cannot hook the contacts when all the solder is in place. Let's do that. So I'm back from desoldering. It looks like this now, just the pins. I have seen there is a manufacturer logo on the side. Oops, light. It is MTI and oops, there is also a type, serial number. Maybe we could find something in the internet about this, maybe about the manufacturer. So let's power it up. I have to move the camera a little bit. You see all the mess I already made. I tried the lowest pin negative, so I go that way. I'll just try it. Oops, it moves. Maybe it's a polarity question. Let me see if I change the polarity. 1, 3, 8. Oh no, it was already 8. That is number 8. Let's go here. Turns to 6 and stays like that. Oops, turns to 9, turns to 7, 5, 3. It looks like we have something century, something common in the center here. So let's see if we can see that. 0. Still 0. Why isn't it working? Am I blocking it? No. Okay, 3. So I just decide to remove that annoying red. Oh, it comes off quite easy. So you have to go. Okay, now we have clean numbers without any obstruction. So turns to 3, it turns to 1, it turns to 9, 7, 5. So we have all the odd numbers. What do we have here? Nothing. 4. 1, 2, no. I think it's a little bit weak. I think I go to 10 volts. How much current do we? Oh, it's only 27 milliamps. Okay, I think that's okay. To go a little bit higher with the voltage. 2, no. So let's go here. So I always change one pin with the positive and then I try all the other pins. So we have something, but not really defined. So I changed polarity. Let's see if that makes something. No. So I think let's go that way. 7, no, 8, okay. 9, still 9, so I don't get any result that I could say this is definitively something. 2, 0, 2, 0, okay. 4, okay. 6, 8. Okay, I think I get it. So if I have the negative on this pin, I can get to 0, 2, 4, 9, 6 and 8. So that means I have the straight numbers, the even numbers, like that. 0 is an even number, maybe. 2 is certainly one. 4, 6 and 8. I'm always counting that position here. And if I get the positive on the same pin, then I get 5, 7, 9, 1, 3. That's all the odd numbers. So that means I have to write that down for the next time. Oops. So we have the number wheel here, which is 4, 5, 6, 7, for example. Then we have the back plate. Oops, you cannot see what I'm drawing here. We have 1, 2, 3, 4, 5, 6 pins. That's the bottom pin. So I go to pin 1, 2, 3. 1, 2, 3, 4, 5, 6. Okay. If I make that pin positive, I get all the odd numbers, 9, 7, 5. So pin 3, positive odd numbers. And if I make the same pin negative, then I get 8, 6, 4, 2, 0. Even. Okay, let's go here. This is 8. That one is 6. We have 4, 2, 0. 4, 2, 0. And if we change the polarity, positive on pin 3, we have 3, 1, 9, 7, 5 is like a little bit, I don't know if you can see that. If I have the even, if I have minus on this and plus on all this other, so I have 0, 2, 4, 6, 8, that's in one row, but on the other side I have 1, 3, 5, 7, 9, which is a little bit weird, but well, I think that's about how this one works. I hope that in the other instrument here, oops, my microscope is in the way. I hope that this instrument, it has the similar mechanical numbers on this side, and I think it has more conductors, so we probably have an easier interface. I hope it has 10 conductors for each rotating number. So I won't disassemble this because I want to keep that, and I think that would be a nice clock. 14:04, like 4 minutes past 2. Okay, I think that's it for today. It's already late. I'm getting tired and I'm talking rubbish. Well, for the other instrument, see the next video. Thank you.